So he will be speaking on the Bayes curve for reflected entropy.
Thank you so much for the invitation. I'd like to tell you about this paper, that one of which came out a few hours back, and one more that should be out soon. For those who've seen a version of this talk before, hopefully there'll be some new things that you learn from this talk as well. Okay, so let me get started. So the motivation behind this work was it was part of this goal of trying to understand the emergence of geometry from entanglement, the program which we like to call 𝗰𝗵𝗶𝗶. And the sort of gold standard of this program has been the Ryu-Takayanagi formula. So the Ryu-Takayanagi formula tells us that the entropy of a boundary subregion, which I have taken to be these two intervals here, is given by the area of the extremal surface that's anchored to the endpoints of the boundary subregion, divided by 4g Newton. And there's been a lot of work trying to generalize this beyond just the area term. There are quantum corrections that become important, and this has been very fruitful in understanding things like the Page curve for entanglement entropy. And so part of the goal that we had was to be able to understand other such holographic connections. For example, the extremal surface has this nice connection to the entanglement entropy, but you might ask about the areas of other such bulk surfaces, which are, say, non-extremal surfaces. And also, in order to understand the entanglement structure better on the side of the boundary, we'd like to understand some other quantities. So, for example, the entanglement entropy is only a good measure of bipartite entanglement in pure states. However, in general, you can have multi-party entanglement, and that can play an important role in the emergence of geometry. And so what we'd like is to have more such entanglement measures that we can understand better, and especially if they have a good holographic dual. So with that, let me tell you about the reflected entropy, which is one such measure. So the reflected entropy is defined by considering this canonical purification. So we start with the density matrix, which is in general a mixed density matrix on systems A and B. And we purify it in a very particular way. So we consider the matrix, the density matrix, and take a square root of the density matrix. This gives us an operator that acts on the Hilbert space of HA tensor HB. And now we think of this as a state which lives on a doubled Hilbert space, which consists of HA tensor HB, which was the original copy, as well as a reflected copy, which is HA star tensor HB star. This is perhaps something that's familiar to people in the example of going from the thermal density matrix to the thermophile double state, which is the canonical purification. So this is just a generalization of that procedure. And then having done so, we define the reflected entropy as the entropy of the region AA star in this particular canonically purified state. So just in pictures, we start with a state which consists of our regions A, B, and perhaps some purification C. We trace out the region C and then consider a purification where we just double the state on AB. This gives us this region AA star, and then computing the entropy of AA star gives us some measure of the correlation between the region A and B in the original mixed density matrix. Okay. Good. Now, this particular measure has the nice feature that it has a very good holographic dual. It was proposed to be a sort of generalization of the Ryu-Takayanagi formula, which involves the so-called entanglement wedge cross-section. So when you compute the reflected entropy of two boundary regions, A and B, which I've taken to be two intervals in this picture, the proposal is that one minimizes over possible cross-sections, which is this red line here, and minimizes them over all possible ways of splitting the entanglement wedge into two parts. So you split it into a part that's homologous to A, and there's a part which is homologous to B, which I've called little b. That gives us, that corresponds to this area term, and then there are, as usual, quantum corrections coming from bulk entropy terms. This was discussed in these set of papers. Why should you believe something like this to be true? There's a simple heuristic argument for this, which is that we can consider a geometry which consists of two copies of the original region. So when we consider region A and B on the boundary, the bulk dual of this subregion is just the entanglement wedge, which is the region shaded gray here. And naturally, when we do this process of reflection, we just consider a doubled copy and then glue them together at the Ryutakyanagi surface. This gives us a spatial geometry which looks like this cylinder with A and A star on one side and B and B star on the other side. Once you believe that this is the bulk dual to the canonical purification, then the entropy can just be computed by the Ryutakyanagi formula. And then the entropy of AA star is just given by two copies of this entanglement wedge. So that's sort of the motivation behind considering this quantity. Now we.
Sorry, I have a question. What if you're below the phase transition? What if AB is small? That what happens then?
Yeah. So thanks for that. So if you're in a disconnected phase, so let's say the intervals are small, then there's no entanglement wedge cross section because there's no surface needed to split them into two parts, and so the reflected entropy is just zero. The entanglement wedge cross section is trivial.
Okay, thank you.
Good. So we can work this out in a little bit more detail beyond this heuristic argument by doing a replica trick. So firstly, in order to do the replica trick, one needs to construct the canonically purified density matrix, which consists of the square root. The square root is hard to construct in general in a path integral. So the trick that we employ is to consider the state, which is rho to the m over 2. If we take m to be an even integer, then this can be constructed using a path integral. And then eventually we would like to analytically continue this parameter m to 1 to get the square root. Similarly, we employ another replica trick to compute the entropy in this state. And that's the more familiar one where we compute the Renyi entropies at integer n and then do some analytic continuation to 1. So in the end, what we want to do is compute this quantity and analytically continue both the parameters m and n to 1. This gives us the reflected entropy. This is something that one can set up in gravity. And the naive guess, which was part of the original proposal, was to do a sort of saddle point approximation similar to what Lukowitz and Maldacena did for the entanglement entropy. However, there are some issues with this proposal. This analytic continuation firstly suffers from an order of limits issue. Note that we have these two parameters that we want to analytically continue to 1. And depending on how you do this analytic continuation, you get different answers. This was pointed out in this particular paper. And so it wasn't clear that there's a principled reason to consider one particular choice of analytic continuation and how to see that it gives the physically correct answer. So that was one issue. And further, as Sukrut just asked, which was when you have a phase transition in the entanglement wedge, the reflected entropy suddenly jumps from a value that's 0 to a value that's non-zero. So there's a very sharp discontinuity in the value of the reflected entropy if we believe the holographic proposal. This indicates that there are non-perturbative effects that are important near this phase transition. And so one would also like to get some handle over such effects in the path integral. And so overall, we need a better calculation in some toy model to be able to understand this issue. Okay. So the toy model that we work with is the so-called West Coast model. This is a toy model that was developed in this paper, which consists of a simple model of Jakob-Teitelbaum gravity, which is 2D gravity, coupled to end-of-the-world branes. So we have an action which has the JT action, which consists of a topological term with parameter S0, and the usual JT action with a dilaton that's coupled to the metric. And further, we add in this term, which is a brane tension mu. And the Lorentzian solutions to this action look like the following. One has a 2D black hole with some horizon and these end-of-the-world branes. The end of the world branes are chosen to have some flavor indices that live on the brain. It's some sort of global symmetry. And we choose to entangle these flavor indices with some auxiliary radiation system. So here we've taken the radiation system to consist of two sets, R1 and R2. And R1 and R2 are entangled in this particular way. So the overall state of the system is such that we consider the black hole in a state with flavor indices IJ on the end of the world brane, and the indices I and J are entangled with the radiation systems R1 and R2. The number of flavors are K1 and K2, and the product K1, K2 is represented by K. So the parameters in this problem are essentially the number of flavors, which denotes the entanglement with the radiation system, as well as the black hole entropy, which is basically the area of the horizon. This can be thought of as a model of a partially evaporated black hole. So you can imagine allowing a black hole to evaporate partially, stopping the evaporation at some point. And then what you have is some radiation in the exterior that's entangled with its interior partners. And so this is some sort of toy version of that picture. Okay, so now in this model, the page transition is basically the fact that we can tune the parameters that denote the amount of entanglement between the radiation and the end of the world brane, which is this log K, to be more or less than the black hole entropy. When it's more than the black hole entropy, this is what we indicate as post the page time. And as is familiar from the work that's happened over the last 2 years, there is a geometric description of this, which corresponds to the entanglement wedge, including an island. So when we look at the regions R1 and R2, they have an island that consists of the interior of the black hole, which gives you the page curve. Now, what does this mean from the perspective of the canonical purification? For the canonical purification, it indicates there's a qualitative change that happens, as we discussed in the case of the two intervals. Before the page time, the entanglement wedge is trivial. And so when we purify the state on R1 and R2, all that ends up happening is that R1 is entangled with its doubled copy R1 star, R2 is entangled with its copy R2 star, and there's no entanglement across these. So if we compute the entropy of R1, R1 star, it's 0, because there's no entanglement across this cut. However, when we cross the page time, then now there's an island for R1 and R2. And so when we consider the doubled copy of this entanglement wedge, it includes a closed universe. This closed universe is made of two copies of the island that are glued together at the horizon of the black hole. And now when we compute the entropy between R1 and R1 star and R2 R2 star, it's non-trivial. Depending on how we tune the parameters, there are two possible so-called RT surfaces in this picture. It's either the orange lines or the pink lines here, depending on whether K1 is less or K2 is less. So in the end, the entropy turns out to be twice log of K1 or log of K2, whichever is minimal. And as expected, we see a sudden jump from 0 to a finite value as soon as you hit the phase transition. This is what the holographic expectation is. And we wanted to analyze this in a little more detail by understanding whether this is really the correct answer. The way we do this is by doing a more refined sort of replica trick, which is called the resolvent trick that was introduced in this paper by Pennington, Schenker, Stanford, and Yang. So we consider the resolvent, which is this function that can be thought of as the generating function of powers of the density matrix. And by the powers of the density matrix can be written down as boundary conditions with integer number of boundaries. And then the rules of the path integral tell you to fill these in with some geometries that are consistent with the boundary conditions. Now, similar to what one does in quantum field theory, you can write down this resolvent in terms of its connected part, which we denote by F, which is similar to what you do with 1𝗶𝗏 diagrams in quantum field theory. And F can be written as a sum over geometries that are connected in this particular way. So you can have one boundary geometries, two boundary geometries, and so on. Once you do that, what we see is that we've now managed to write the resolvent in terms of a function of the resolvent. So it's a self-consistency equation or a Schwinger-Dyson equation, which you can solve. And this was solved in the original paper to find an approximate entanglement spectrum. The approximate form of the entanglement spectrum is simple. It essentially takes the form of a cutoff thermal spectrum. You take the thermal spectrum, look at its first k eigenvalues, and cut off the spectrum at that location and shift it appropriately to make it correctly normalized. The details of this are not so important, but the important fact is that solving this resolvent trick gives us the entanglement spectrum. Now we can do the same thing for the reflected entropy. So we consider the reflected entanglement spectrum, which is the spectrum of the density matrix rho R1 star. The way we do this is by generalizing the resolvent. We consider the state rho to the m over 2, which was prepared by some path integral for even integer m. And then we do this thing where we flip bras to ket. So we consider a state that's prepared here, and then its Hermitian conjugate. By tracing out the R2 star legs, we end up with the density matrix on R1 star. In short, what ends up happening is that a particular component of this resolvent gives us the correct resolvent for the density matrix. Now, I can't go through all of the details, but just briefly to mention what we end up doing is that there's a diagrammatic summation over a class of planar diagrams. So you get some boundary conditions for this resolvent. You can look at all possible geometries that fill in those boundary conditions. And we can classify them based on their weights. And there's a particular class of planar diagrams that we conjecture will dominate, and these include a lot of replica symmetry breaking effects. So they have there's a particular class of saddles which are important. There's evidence for this class of diagrams by looking at certain asymptotic behaviors, and also we have evidence from numerical calculations, and also similar effects show up in our tensor network calculations, which you can find in the paper that appeared today. And so there's a significant amount of evidence for this being the correct resummation. Once you do that, then you end up with a solution to this Schwinger-Dyson equation, which you can solve self-consistently. And you end up with a simple entanglement spectrum. So let me just explain in detail what the spectrum turns out to be. The spectrum has a simple form where it has two main features. So the spectrum has one pole, which is a single eigenvalue. The single eigenvalue can be thought of as corresponding to the disconnected sector. So when we are far into the disconnected phase, we end up having a geometry that just corresponds to R1 being purified by R1 star, R2 being purified by R2 star. And since there's no entropy, you expect it to be a single eigenvalue since it's a pure state. That's this feature. On the other hand, there's another feature, which is a mound of eigenvalues, which has a number of eigenvalues that's roughly k1 squared. And it's a very sharp peak. And so when you compute the entropy for this mound of eigenvalues, you'd get something which is twice log k1. This is the answer you'd expect in the connected sector. So in the connected sector, remember that there was this closed universe which was causing it to have a non-trivial entanglement across the R1 star cut. And it gives you precisely this answer of 2 log k1. However, what we find here is that this was true far on either phase, but here we see that these two features persist no matter where you are in parameter space. All that changes is the weights, which we've denoted by PC and PD, the probability of being disconnected or connected, which interpolate across the phase transition. So depending on these weights, we get a reflected entropy that's basically given by the probability of being connected times the answer in the connected phase. So all I need to tell you to explain the phase transition is what these probabilities do. The probabilities can be computed analytically in terms of the Renyi entropies of these systems. Q here denotes some parameter which essentially tells you on which side of the phase transition you are. So as you increase K, Q increases. And so you're far on the connected side of the phase transition, whereas for small k, for small q, you're on the disconnected part of the phase transition. The transition happens exactly at q equals 1. So if you look at this plot, what you see is that the probability of being connected is really small for small q, and it increases around the time when the phase transition happens, and it becomes 1 at large q. Now, what I've plotted here is two different curves. The red curve corresponds to the microcanonical ensemble, where the energy of the black hole is fixed, and this gives you a very sharp transition. However, the blue one corresponds to the canonical ensemble, where you have thermal fluctuations. And since thermal fluctuations basically tell you that there are fluctuations in the horizon area, the transition happens at different locations depending on which area you're at. This has the effect of spreading out the phase transition over a large region. And so this is similar to what was found in the case of the page curve for entanglement entropy. So we find something that's very consistent with this proposal. Now, we also consider the Renyi versions of this reflected entropy. And the Renyi versions show a novel feature. The novel feature is that the phase transition shifts depending on this Renyi parameter. The location of the phase transition depends on this Renyi parameter m. For m greater than 1, we're essentially considering temperatures that are slightly lower than the temperature of the black hole. So the area is smaller, and so the phase transition happens earlier. So at a smaller value of k, you see these thicker curves which undergo these transitions, and this corresponds to m greater than 1. For m less than 1, we find that the phase transition happens later, and this is expected because m less than 1 corresponds to weighing the higher temperatures more, and hence the phase transition happens later. But as an aside, in order to do this calculation, we had to compute the Renyi entropies in this model. And there's an interesting feature that for m greater than 1, one finds a nice Ryu-Takayanagi-like formula. This was something that was proposed by Ji Dong about 5 years back. However, for m less than 1, there's no analog of this Ryu-Takayanagi-like formula, and you find large corrections over a large region of parameter space. This is something that I think should be explored more in future. Okay, so with that, let me summarize. The gist of the talk was that this proposal that the reflected entropy is equal to twice the entanglement wedge cross-section works in this toy model. There were various issues with this proposal that were hard to handle in situations where you can't do the gravity path integral completely. And in this particular toy model, the fact that the Joydeep-Teitelbaum gravity path integral can be done explicitly helps us understand a lot of these issues. So having demonstrated that this holographic proposal works well, we can also understand better the procedure for analytic continuation. The analytic continuation that gave rise to this entanglement wedge cross-section proposal was we had these two parameters n and m, and what we had to do was analytically continue n to 1 first and then m to 1. And in this model, there's a good reason for this, and we can show this explicitly. And the resolvent trick resolves this issue. Further, we found that there were these fluctuations near the phase transition because of replica symmetry breaking saddles, which gives some important non-perturbative effects. This smooths out the page curve for reflected entropy over a large region. And we expect that similar features should show up in other examples in ADS. So when we have two intervals as well, there's this phase transition, which goes from the disconnected phase to the connected phase. And we expect such thermal fluctuations to be important there as well. There's a similar calculation that we did in tensor networks, which you can find in the paper that appeared today. And there we find similar features, but there's also a richer spectrum. So there's more things we can do in those models, but the story overall remains quite similar. So with that, I'd like to thank you.
Okay. Very nice talk, Pratik. You also finished in time, actually. So we have about 5 minutes for questions on this talk. Yeah. So we have Sukrut Raju. Yeah, a hand raised.
Yeah. Hi, Pratik. Thanks for the nice talk. So I had a slightly tangential question. So in this model is kind of an unphysical model, right? Because you have these flavor indices on the brain that don't actually interact with gravity. So I understand you can define the model well by just thinking of a Euclidean path integral with decorated boundaries where you add some flavors. But I mean, do you have any feeling for how these calculations would change if you made it more physical by really adding interactions between these degrees of freedom on the brain and the ambient space? I mean, would that change anything, or do you think that might be important?
Yeah, that's a good question. So I think like qualitatively, at least for the calculations we did, I don't think much will change. For example, in the case of the entanglement entropy, there were these questions about this same issue that you talked about. There's a global symmetry of these flavors on the brains. And there were some papers which did calculations which refined that, and they basically found the same sort of page curve, and nothing much changed in that context, at least. So I expect that for the reflected entropy as well, the calculations will go through in a similar way. But of course, it's a good question. Like I would like a more realistic model where we can do this calculation explicitly.
Yeah, there is another question from Onkar Parikar.
Hi, Pratik. Thank you for the nice talk. Quick question: do you imagine one could like consider multi-party entangled states of like the CFT dual itself without having this radiation sort of bath lying around? And would you think that sort of gives a more like a physical entanglement wedge, like a geometric entanglement wedge cross section in these models, as opposed to having like lines cutting through this? Is there some way to like have a geometric cross section in these models?
Yeah, in 2 dimensions, I don't know exactly how to do it. At least in Joydeep tidal point gravity, I don't know of a situation where you have an island and it gets like. There's a slightly refined version of this, which is the East Coast model, where you have Joydeep tidal point gravity coupled to like flat space. There you do find this feature. It was pointed out in this paper by myself, Masamichi Miyaji, and Ven Chandrasekaran. So in that context, even though it's not exactly an answer to your question, because you still have this auxiliary bath region, but you do end up getting a geometric cross section. So you have an island, and there's a geometric cross section at the middle of the island. So that's a slightly better version of this. But yeah, maybe in higher dimensions with something like a doubly holographic model, you'd find something like a geometric cross section.
I see. Thank you.
Thanks.
Okay, so I think there is no more hands raised. I have a very trivial question. That you are calling this reflected entropy. In what sense this is reflected? You have a system A and they are sort of disconnected on boundary, but why you call that reflected? I mean, this would reflected be a joint entropy, which is the entropy of both system A and B, which are disjoint in some sense.
So we could have done something like, we could have taken like one of the regions A and computed its entropy. That would be a different measure of entanglement. The reflected came from the fact that because we had a mixed state, we traced out this C, and then we reflected it to consider this other copy, which was A star and B star. So the reflected was just saying that the reflection was part of the purification that we used to define this entropy. That's all that the definition meant. Like even here, like geometrically, we see that we have this single model where we have one copy of this wedge, and the reflection indicates that we just get this doubled copy where we glue them together. The reflection is just, it's this conjugate symmetry.
So it's a way of integrating out your C from the from your entanglement wedge of the two.
Yes.
Yes.
Sorry, I missed the last part.
Okay, so I think there is one more hands raised by Deepan Betal, please.
Yes, sir. Yes, sir. Am I audible?
Yeah.
Is it in the entanglement wedge figure over there we can consider C as a bath, right?
In this figure, you mean?
Yes, sir.
Yeah, you can think of C as a bath if you like. Yeah, it's basically what's purifying the state on A and B. Yeah.
Okay, sir. So if the Hawking radiation interacts with the bath, will that cause any kind of change in the area of the entanglement cross section of AB?
Sorry, in this model, I mean, in this picture itself, I was just considering pure ADS. There was no Hawking radiation here.
In the case where you have the island and we.
In the case where the island, yeah. So in this example, we were considering, like, this is probably related to Surat's question, like we were considering a very simple model where there were no interactions. All we did was we assumed there were some interactions that led to this entangled state. So there was some process which generated this Hawking radiation. And then we were just looking at the entropy at this fixed time. Like there was no dynamics. But in order to generate the state, there must have been some interactions that led to this. So it's sort of secretly hidden in this original state that I talked about.
So if we take different instances of time, could that expand the entanglement wedge and hence changing the eigenvalue spectrum we had shown with the pole? That
this one, sorry, this one.
Yes. Could that expand the one of the connector region Could it expand it a bit if we check at different times?
Qualitatively, like as long as you're at late times and you have an island, you'll be in this connected phase even after time evolution. And the dominant thing will be this mound of eigenvalues. If you're pre-page time and you don't have an island, then you're right that this thing will dominate.
Okay. Thank you, sir.
Okay, I think there is one more question from Arnav, maybe shorter one. Yeah, please.
Hi, yes, I'll just ask a very quick question. First of all, thanks a lot for a very nice talk. So my question is, instead of considering, doubling the system, you could have considered n copies of this, right? I mean, and of course, it will get into this multipartite entanglement and so on, about which very little is known. But I'm just wondering whether that's a useful way to think about it.
Yeah, we could. Actually, there are such measures that have been considered. So people have talked about these generalizations of the entanglement wedge cross section, which are supposed to correspond to. So you start with some many party system and then glue them one by one in some very complicated way. That gives rise to these like tripartite and four-partite cross sections. But the problem is we still don't understand the boundary dual of these things. So it would be nice if we can construct some boundary dual, which was nice. Like in this context, the reflection was sort of unique. Like we just took this density matrix, and the density matrix has a natural purification on a doubled copy. But maybe there's some other complicated thing you can do where it becomes on n copies and then compute some other entropy.
As you said, it's probably not unique. There could be many embeddings and so
on. Yeah, but if like in this case as well, like the purification aren't unique, but there's something nice about this particular purification. So maybe you could, in the n-party case, also find something that's consistent with, say, some permutation symmetry of the systems or something like that, and that might be unique. I'm not sure.
Okay, thanks a lot. Thanks.
Okay, so let us thank the speaker for very nice presentation. Our next speaker is Joydeep Chakravarty.
Hi, thank you. Should I share my screen?
Yeah, please share. Yeah.